Hello, Calculus 1 students. This is the first part of our review for our second midterm. We will be going over a sample test. We will see different problems on our actual test. So make sure you see Canvas for more review materials. But we get started with number 1. We have a particle moving on the xy plane, and this is its position vector. T cosine t, comma, sine of 2t. The first part, find the velocity at time t. Well, we need to differentiate each coordinate. Maybe I'll come to the side and differentiate the part that involves product rule. So if we differentiate t cosine t, this will be, as I said, product rule. We have first times derivative of the second, and then plus the second times derivative of the first, like this. So now let's just write our answer. The first coordinate, well, it's minus t sine t plus cosine t. And the second coordinate, well, we differentiate the sine of 2t. And this is technically chain rule. We will have 2 cosine 2t. This is the velocity vector. Next part, find the acceleration of the particle at time t. Once again, this will be a vector. What I need to do is differentiate the first coordinate and then differentiate the second coordinate to get the two components of this vector. Well, let's come to the side and differentiate minus t sine t plus cosine t. This is a sum of two terms. The first term, product rule. So we have first derivative of the second, and then plus the second derivative of the first. Now differentiate the second term. Derivative of cosine is minus sine. So you have minus sine t. And maybe I can move this up. You see what we get here. We have minus t cosine t, and then minus 2 sine t. So this goes in my first coordinate of the acceleration vector. Okay, we have minus t cosine t, minus 2 sine t. Now, differentiate 2 cosine 2t. Well, when we differentiate this, we have 2t as an inside function again, so we will be multiplying by another 2. We get minus 4 sine 2t. Okay, wonderful. Next question. We want the speed of the particle at t equals pi. Well, step number 1, we can find the velocity at t equals pi. Velocity is this one. So this will be minus pi sine pi plus cosine pi, comma 2 cosine 2 pi. Well, we need to evaluate these. Okay, the sine of pi is 0, cosine of pi is minus 1, and the cosine of 2 pi is 1. Put that all together, you see what we have. We have minus 1 and 2. This is the velocity at time t equals pi, but the speed is a number. It's a non-negative number, and the speed is the length of the velocity vector. And so let's calculate this now. If we calculate the length of the velocity vector, well, this is a square root, and then we square each component. So we have minus 1 squared plus 2 squared. You notice underneath the square root is 1 plus 4, and so the answer here is the square root of 5. Now, last part, we want an equation of the tangent line to the trajectory at t equals pi. Well, first of all, we need a point. This we just evaluate. This will be pi cosine pi, comma, sine of 2 pi. So let's write this. We have pi cosine pi, comma, the sine of 2 pi. Cosine of pi is -1, so we have negative pi. Sine of 2 pi is 0. This is the point that is on my trajectory, also on my tangent line. But now I need the slope. We have dy dx evaluated at t equals pi. And how we calculate this? Well, it's just y prime of pi, I'll write it this way, divided by x prime of pi. Now, in fact, we have this already calculated. It's here. We can read off y prime and x prime in our velocity vector. Here's y prime of pi, and here is x prime of pi. So now let's take the ratio. This will be 2 over -1, which is -2. Well, we have a point, we have the slope, and so we can write an equation for this line. It will be y minus 0 equals m x minus pi, or x plus pi. And so this is it. Y equals -2 times x plus pi. Now, let's move forward. Number 2. Well, we have 3 indefinite integrals here. This is not substitution. Well, what I need to do is write this as a sum of terms where each term is coefficient times some power of t. And the way we get started on this first part is we need to distribute the -4 across the parentheses. So let's just rewrite. I have not integrated yet. I'm just rewriting. T to the -4 times t cubed is t to the -1. T to the -4 times t to the 8th power is t to the 4th power. And then I have -2. This power, in the denominator, I have a 7 over 2. So this is t to the -7 over 2. Okay, that was the work of rewriting this integrand as a sum of terms, where every term is coefficient times power of t. Now, not all of these are power rule. In particular, this one is not. When we integrate t to the -1, well, this is the integral of 1 over t dt, which is ln absolute value of t. In fact, let's write this. We have ln absolute value of t. This next one is definitely power rule. Add a power, divide by the higher power. And the third term is also power rule. We have a -2. We add a power, which will be -5/2. Divide by the higher power, -5/2. Now, we typically do not leave fractions in the denominator, so let's just rewrite this last term. I'll do it in my answer blank. We have ln absolute value of t plus t to the 5th over 5. This one, when we invert and multiply, you notice it's plus 4/5. We have plus 4 over 5, t to the -5/2, plus c. So this is my final answer to this question. Letter B. This is substitution. Up inside the exponent of b, I see something more than just an x. Moreover, I have a multiple of its derivative in my integrand. So u is the secant of y. Du, well, we take the derivative. We have secant y, tangent y, dy. Now you notice, handed to me in my integral, I have exactly du. So I typically will put a box around this part. Now we have an integral. This is e to the u du. Okay, integrate. When we integrate e to the u, we have e to the u plus c. Final step, go back to y. So we have e to the secant of y plus c. This was integration by substitution. Well, the next one is also integration by substitution. Once again, you see we have this inside function. More than that, we have a multiple of its derivative in our integrand. So u is going to be x to the 5th plus 9. Du, well, we take the derivative. We have 5x to the 4th dx. Now, We don't exactly have du. What do we have in our integrand? We have x to the fourth dx. You see this is 1 over 5 du. So this was an important step. We find our multiplier. Now let's convert to an integral of u. So we have an integral. We have sine u times 1 over 5 du. Now integrate. We integrate sine, we get negative cosine. Final step, we go back to x. So we have minus 1 over 5 cosine x to the fifth plus 9, and then plus c. This is our final answer here. This was integration by substitution. Number 3, we want to differentiate g of x, do not simplify. This is really a test of, are we able to realize what rule to use and correctly apply the rules? So the first term, 2 to the tangent of x, I will differentiate term by term. So this is chain rule. We have derivative of the outside, which is like this. Then we evaluate at the inside function. Multiply by the derivative of the inside function. Derivative of tangent is secant squared. We have secant squared. Okay, then we put a plus. Now we differentiate the second term. Maybe I should rewrite this. This is sine inverse of 3x to the 1/2 power. So this will be chain rule, in fact, 2 times for this term. So we bring down the power minus 1. We put in the entire inside function, sine inverse of 3x. Now, multiply by. I need to differentiate the sine inverse of 3x. First, we have the derivative of sine inverse, which looks like this, squared. Okay, put in the entire inside function, 3x. And finally, multiply by the derivative of the inside function, which is 3. So this is a long derivative because it had 2 terms. Maybe I'll make each one smaller so we can fit it on this one line. That was number 3. Now number 4. Oh goodness, this is our optimization problem. These are really fun, but I understand students struggle with these. We want to build a rectangular box. The length at the base of the box is 3 times the width, and the box has no top. We are given the volume, and we're given information about the cost of the material for the sides. We want to minimize the cost. First, we draw a picture. Here's a great picture. We have x by 3x by y. Now, we know the volume, so let's write this down. You notice the volume, you take 3x times x, which is 3x squared, and then times y. You take length times width times height, and this will be 243. You notice this is an equation, and this is my constraint equation. What else do we have in this problem? Well, we need an objective function, and this will come from the cost. So there is no top. The base costs $4 per square foot. So we have $4 per square foot times the area of the base, which is 3x squared. So this is the cost for the base. Now, what about the cost for the sides? These are $1 per square foot times, well, we have this side and this side are both 3x by y. So that would be 6x times y for the 2 areas. Then we have this and this are both x by y. So we have 2 more x times y's. Altogether, we have an 8xy. That is from the sides. And this is my objective function. Okay, how do these problems go? Once we have our constraint equation and our objective function, oh, maybe I should write above, this is from the sides. We use the constraint equation to solve for one variable in terms of the other. It's going to be easier to solve for y in terms of x. So here y will be 243 over 3x squared, which is 81 divided by x squared. Now, we can write cost as a function of x by substituting in this expression for y. So altogether, you see I have 12x squared plus 8x times 81. I'll write it this way, x to the minus 2. And let's simplify this. This is 12x squared plus 81 times 8 is 648, x to the minus 1. And this is defined, let's see, we need x and y to both be positive, but if you stare at this equation, x could be any positive number and we could find a y that will make a box. So this is defined on the open interval 0 to infinity, and we are wanting to minimize. Now we're ready for the calculus part of this problem. We have a differentiable function on an open interval, and we are looking for critical points. So let's do this now. We take the derivative. We have 24x minus 648, x to the minus 2. This is certainly defined on the whole open interval, so the only potential critical points are where the first derivative is 0. Okay, so 0 is c prime of x. What do we get from this? It says that 24x equals 648 x to the minus 2. At this point, I can multiply both sides of the equation by x squared. I can also divide both sides of the equation by 24. So I get on this side x cubed, and on this side I get 27. We can solve here. We have x is the cube root of 27, or 3. The nice thing is this is our only critical point. So we have one critical point on an open interval. We can use, say, second derivative test to make sure we have a minimum. Let's do this now. The second derivative is 24 plus 2 times 648 x to the minus 3. Now, evaluate at my critical point. I get 24 plus 2 times 648 divided by 3 cubed. You notice I'm just adding two positive numbers. So this is definitely positive. This says concave up. I draw a picture, and I see, in fact, I do have a min at 3. Okay, are we finished with the problem? Well, not exactly, because I still have this answer blank. The very last step, what are we asked for? We want the cost of the least expensive box. And you can even see, I tell you, minimum cost, we are reporting back C of 3. This is 12 times 9 plus 648 divided by 3, which is 324. But this is our final answer here. That was a fun problem. Number 5, we have two questions that involve limits. And if we use L'Hopital, we need to state where we use it. Okay, wonderful. So let's think about both of these first. The first is limit at 1, and the second is limit at infinity. So at 1, here, what happens in the numerator? We get 10 minus 1 minus 9, which is 0. And in the denominator, we have 3 times the log base 5 of 1. Well, the log base a of 1 is always 0 because a to the 0 gives us 1. So in fact, we have 0 over 0. In fact, L'Hopital's rule applies. So let's mark it. This is part of it. Now, L'Hopital's rule says that two limits are equal. Not that this function equals another function, definitely not. But at 1, the limit as x approaches 1 of this will be equal to the limit as x approaches 1, where we take the derivative on the top and take the derivative on the bottom. So let's do that here. When I differentiate the top, I get 10 minus 2x. 10 minus 2x. Differentiate the bottom. This is a log base 5. So I have 3. I have 1 over x times 1 over ln 5. Now, reevaluate the limit. Let's see what happens. Okay, as x approaches 1, what do I get here? Well, the numerator, I get 10 minus 2, which is 8. The denominator, I have 3 divided by ln 5. Now, the only thing is we don't leave fractions in the denominator, so we need to invert and multiply. Here I get 8 natural log 5 divided by 3. This will be my final answer. In fact, maybe I will just move it into my answer blank. This limit exists and equals 8 ln 5 divided by 3. Next question. This is a really great one. What's happening here? First of all, maybe I will do this on the side. What happens as x goes to infinity of e to the 5 over x? This is something we need to think about. Really, this is a bring the limit inside a continuous function question because, well, this will be e to the limit as x approaches infinity of 5 over x. 5 over x approaches 0 as x grows without bound. So we get e to the 0, which is 1. Okay, now I'm ready to return back. I'm going to leave this because I need it. I'm ready to return back to the limit I'm asked about. Just do this and do this. What do you notice about this question? Well, the numerator, 1 minus 1. The denominator, 5 over x, approaches 0. So we, in fact, do get 0 over 0. Which means we may use L'Hopital. We mark L'Hopital. And then we will take the derivative on the top, take the derivative on the bottom, reevaluate the limit. Let's do this. So we will have a limit as x goes to infinity. Well, you see the numerator? I really have a chain rule because up inside the exponent is something more than just an x. Now, we also see that 5 over x in the denominator. So, let's see, this is sort of more side work, is here. When we differentiate 5x to the minus 1, I've left this off. We have minus 5 over x squared, power rule. Okay, so now let's jump back into this question. We differentiate e to the 5 over x. We get e to the 5 over x times minus 5 over x squared. Now differentiate the denominator. We have minus 5 over x squared. But you see now, this next equals is not L'Hopital's rule. Because I have the same thing in the numerator and denominator, I can just cancel them off. So this will be a limit as x goes to infinity of e to the 5 over x. So we don't mark this LH. That was not L'Hopital. I just canceled these off. Well, this is our side work. We've already done this, so the answer is 1. That was a fun one. Took L'Hopital. Also, bring the limit inside a continuous function. Wonderful. Number 6, we have a definite integral, and this involves substitution. One place we look for inside functions in the denominator, and this will work here because we have x squared minus 3. Moreover, we have a multiple of its derivative in our integrand. So let's start writing out the work for substitution. U is x squared minus 3 du. We have 2x dx. Now handed to me in my integral is 4x dx. You notice this is 2 du. Now, I change my limits of integration to u limits. Okay, always, it's easier for me. My x ranges between 2 and 3. And u here will be 2 squared minus 3, which is 1. Here u will be 3 squared minus 3, which is 9 minus 3, which is 6. So I will put all of this in a box. Okay, now I'm ready for the problem. We're ready to convert to an integral of u. It's an integral. U ranges from 1 to 6. And then I have 1 over u times 2 du. We have 2 ln absolute value of u, and then we evaluate between 1 and 6. We have 2 ln 6 minus 2 natural log of 1, so we get our final answer. Natural log of 1 is 0, so we just have 2 natural log of 6. Number 7, this is the last question. we want to evaluate the right Riemann sum for this function, f of x, on the interval -4 to 6 using 5 subintervals of equal length. Step 1, write down delta x. This is always, well, if this is little a and this is b, it will be b minus a over n. In this case, we have 6 minus -4 divided by 5. Next step, write down your partition. We start at the left endpoint, which is -4. We march forward by delta x until we hit the right endpoint. So we have -4, we have -2, 0, 2, 4, and 6. And we could check. We have 1, 2, 3, 4, 5 subintervals. Or if you think about points in the partition, you always have one more point in the partition than you do subintervals. Here we have 6 points. Next, right Riemann sum. We use the right endpoint. So the right endpoints are here, 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 here. So I could write this in summation notation. It would be a sum, I equals 1 to 5, f of the right, which is xi, delta x. What I will typically do is factor out the delta x from the sum. So this will be 2. And then, okay, I'll do this in 2 steps. We have f of -2 plus f of 0 plus f of 2 plus f of 4 plus f of 6. This is it. This is my right Riemann sum. Now let's just write what this is for my specific function f. So I have a 2. Okay. Then evaluate my function at -2. I have 4 over 3 plus evaluate my function at 0. This is 0. Plus, evaluate my function at 2. I have 4 over 7. Plus, evaluate my function at 4. I have 16 over 9. Plus, evaluate my function at 6. I have 36 over 11. Very last step. We enter this entire thing into our calculator as one line, then we round. So I have this here, which I just entered into Desmos. You see, this is how you should enter it in your calculator. One line, and then we round to 4 decimal places in this case. So rounded to 4 decimal places, we see our answer, it's 13.9105. This would be my final answer here. And this is the end of the first sample test for our second midterm. Thank you so much, students.